Alright, I think we're back. And everything should be fine. Okay, well. Atelier Rorona. We are continuing. In addition, due to popular demand, my lectures are well shop opinion. In a bit. There are some things I do have to get done first. Also, my my teaching assistant is in the shower, so we're just gonna play the game for a bit, you know? Give it some time of just playing the game properly and not talking about computers. What are we on? Third quest, ancient stuff. Before we ended last time, I was going to turn this stuff in. Which we can do that now. Oh. I already completed the stamp sheet. 3, 6, 9, what does I have?
納品する品を増やすんだろ。どれを納品するんだ?
Hopefully this is enough soap. Hopefully. Okay, it was enough soap.
では、期限の日まで大切に預からせてもらう。
Alright, well that works. Right, I assume the little stamp sheet is done. Yes, may have fingered already.
こんにちは。今日はどんなご用？そうそう、ティファナが感謝してたわ。依頼やってくれてありがとうって。私からもお礼言っておくわね。
Oh, that's always nice. I need cash though. Cash. I mean... it is kind of suck getting rid of this. Bag bomb. Tink. All the stuff I don't have right now. That's probably fine. Oh, still that one. Okay. I guess we just kinda make some stuff. I am just kinda checking around. Nothing new should happen until the end of the term. I guess I can buy this guy cabbage soup. Okay. I don't even know what we have that we can make. All this stuff apparently. I mean, none of this is like particularly important right now. Nope, wrong button again. I will look into armor, but...
Oh,
Trendy stuff we still haven't made yet. Pink. Skirt. Nylon feather still goes. Can't tell if any of this is good or not. I mean, I guess we can make that. I guess we'll wait. I don't really need it right now. Yeah, we don't particularly need any of this time. Strong bullet. Dang, it's just like automatically better than the one I made. Fine, I guess. Convert, quality, defense +3. Wait, does it also have defense +3? Attack +3. 16, 3. Attack +5. Oh, sturdy must do that. That's why. I mean, I guess it's fine. Well, you know, I'll keep the one I made. I'll keep the one I made. No, we're fine. In terms of things we like absolutely need, I mean, is there anything at the mines we don't need? I feel like everything else we have like plenty of. Yeah, we're just gonna go through the motions. I assume we're going to need most of this stuff. Field art. Oh, there's a guy here. I forgot. Oh, this guy. Oh, this is nothing. They'll be in the future, huh? At least at this point. Eventually we'll have a lecture. Eventually. Give it a little bit. We do need to get some gameplay in after all. I also have a few more things to set up before then. Gemstone, yeah. Never hurts to have ore.
Oh, 出てきやがったな。ちょろいぜ。当たりやがれ。楽勝楽勝。 ろいぜ。そら
この
ちょろいぜ。そらま、こんなもんだな。
Seriously, why is this website so bad? Trying to log into my stuff. Oh. Did not see that one coming. Services. E-learning.
どうだ。
私の手にかかればこんなもんよ。
Does that get me there? Okay, that gets me there.
やったね。レベルアップふん。
I'm just pulling some extra notes up for now. What was this one? Oh yeah, it's always the bomb, wasn't it? Alright, 14 days. Okay, there we go. We do need progress. Oh gosh, that was always one of the consistent quests.
お、出てきやがったな。
Wait,
行くわよ。
当たりやがれ。ちょろいぜ。
この私の手にかかればこんなもんよ。
this really takes a long time to load. Yeah. Only one glow press. Okay. That's a required fight. I almost could just be killing everything when I'm here.
さあ、どっからでもかかってきなさい。この
当たりやがれ。
いたた。この私の手にかかればこんなもんよ。
Who would have thought? Huh, when did that person show up? 6 seconds. Interesting. Imagine popping in for exactly 6 seconds.
出てきた。狙われてる。
気をつけろよ。そら
いて。この
どうだ。
狙われてる。
気をつけろよ。ちょろいぜ。ちょろいぜ。気をつけろよ。ちょろいぜ。そら
Okay, hold on. I'm having a hard time searching my notebook.
よし強くなってきたぜ
right. Where did I put these? No, that's for machine learning. Where are my OOD notes? Oh, there they are. They're past the digital logic ones. Okay. My notes are ready. Just waiting for my TA.
さあどっからでもかかってきなさい
Some articles on how to study some of the stuff that are on here.
この
当たりやがれ
どうし
気
よう
をつけろよちょろいぜ
I guess I can get through some of the, what's it called? Some of the nice, not so nice content while nobody is here. the things that I was much less likely to include in my own notes. Hence why I have the PowerPoint up right now. Let's see. Object-oriented analysis and design. From the Larman textbook. Okay. Just trying to see where I feel like starting. Okay, it does really kind of get straight into the meat of things, huh? I guess the dates, the stuff like the things like the dates aren't like amazingly interesting when you're just kind of looking at them on their own. Okay. So for those not aware, object-oriented design is a method of kind of organizing your software. It helps a lot with the process, so to speak. Let's see, how to define it without going into too much detail. I will say this does require some minimal knowledge in the fact that software exists and that code is required to be written in order for software to work. All the little things. So yeah. Thinking in terms of objects. That's also another just like basic thing that I have to wait for. Alright, but the actual real dry stuff. What is this? Dahl and Nygaard. 1967 from the Norwegian Computing Center. They created Simula. Kind of one of the first major ideas for implementing an object-oriented system, which prior was always problems were normally either solved with functional decomposition, which breaks a series of tasks into smaller pieces, functions, if you will. So if you needed, say, just a random piece of functionality that doesn't need to be within your main, you just throw it off to a whole separate function, call the function, get the value you need back. Everything kind of looks neater, everything is simpler, it's all easier to understand. Or the other approach, which is to not plan at all. To just use no design at all. Which, I think it actually includes a study on here. Somewhere. Oh, there you go. A study in 2004. Object-oriented techniques were used in only 30% of the companies studied. Or I guess probably not necessarily companies, but projects. I think, because projects are what actually get completed. The most dominant practice was to have no technique at all. Just have no planning for your software. Just getting your problem
私の
and
手に
running
かか
with
れば
it.
こんなもんよ。
Which, as inefficient as that might sound, that's kind of how a lot of stuff happens. Okay, back to this. 1972, we have what is considered by most source text to be the first object-oriented, first properly object-oriented programming language, which went under the name of Smalltalk. I don't think it still exists, or if anybody still like programs in it, or anything like that.
さ
But
あ、どっからでもかかってきな
that
さい。
was kind of the first, so to speak. After that, we have a whole series of other names and dates. What is that? Grady Booch created a book called Object-Oriented Design in 1982. Just 6 years later, Bertrand Meyer created very creatively named Object-Oriented Software Perspective, which, as you'll learn, we're not great at naming things. Miller and Schler, also 1988. Object-Oriented Systems Analysis. Again, very creative. I always like how computer scientists name things. Jump forward exactly 2 years. So, the study of object-oriented design it's constant. Since it kind of came into the ideas, they've been kind of researching it, testing it out. Because in theory, it can make things a lot easier. It can make, changes in your project's requirements significantly easier to handle. Provide more modularity for things like debugging. Increases readability for people who have to come after you. Which, depending on who you are, may or may not be a benefit. It is actually a thing sometimes where people make their code intentionally difficult. Intentionally difficult to understand simply so nobody else can come after them and take their job. Which, I guess in some cases isn't exactly inaccurate, but it is a little bit annoying. What else? Designing object-oriented software, yeah, that was 1990. Object-oriented analysis in 1990. Object-oriented design in 1991. All these books, all aptly named, so to speak. Which I guess that makes sense when it comes to like textbooks on studies and things like that. You're usually very specific. Almost like annoyingly so, if you read any of them. Like scholar articles and whatnot. They're all pretty on the nose of how they're named. Oh, cutscene.
あ、気のせいかな。誰かに見られてた気がするんだけど。危なかった。危なかったじゃないでしょ。あの子に会いに来たのに隠れてどうするのよ。だって恥ずかしいし。
だったら初めから来るなって話だけどな。
ずっと隠れてるわけにもいかないでしょ。ほら、覚悟を決めて。うん。よし。
何をしている？
すみません。怪しいものではないんです。こちらのアトリエに用がありまして。
おっと、見るからに怪しいなんて使い古されたツッコミはなしだぜ。
よくわからんが、用があるならさっさと入れ。
まだ心の準備が。
ロロナ、客が来てるぞ。
エちゃんとホロくんの。
おいおい、リオネラだけさん付けかよ。
ごめんなさい。ホロさん。
逆だ逆。こいつはさん付けするほど偉くないって言ってんだよ。
そうそう、もっと気楽に接してあげてちょうだい。気楽に。じゃあリオちゃん。リオちゃん？嫌かな。嫌だったら他のにするけど。嫌じゃない。あだ名で呼んでもらったの初めてだから驚いただけで。ならよかった。それでリオちゃん、何か私に用事？この間ちゃんとお礼言えてなかったから。ありがとうございました。
Ah, welcome. I say welcome as if I am surprised to see you. People of the future, this is my my TA, my teaching assistant. I don't know what you want me to refer to you as here, just tell me in chat or something. We are in the middle of the cutscene, so you came at a suboptimal time, but it should be over soon.
そんな、別にお礼なんてよかったのに。
TA, okay. From this moment forward, he is now known as TA.
あと錬金術師ってのがどんなもんなのか興味があってよ。怪しげな建物にでも住んでるかと思ったら意外と普通なんだな。
なんでも町の人の依頼を受けて生計を立ててるとか。もしよかったら私たちも近いうち何か依頼に来るわね。本当？ありがとう。私にできることなら何でもやるから。私そろそろ帰ります。
はあ？まだ来たばっかじゃねえか。もっとゆっくりしてこうぜ。
Just out of curiosity, how is your paper going?
でも私もうまあリオネラにしては頑張った方かしらね。ごめんなさいね。この子人見知りなものだから。気にしないで。それじゃあまたね、リオちゃん。また。
It was more than one page. Okay, so it was one page earlier today. Honestly, it was a little bit more than one page. But I revised it, so now it's back to one page. Hey, you're not supposed to be moving backwards, you're supposed to be moving forwards.
ずいぶんと変わったお友達だな。
そうですか？普通の子だと思いますけど。
お前の普通の基準はよくわからんが、あれはなかなか面白い娘だ。気に入った。近いうちアトリエに遊びに連れてくるといい。
気に入ったって、まさかリオちゃんに変なことする気じゃないよね。
Oh, there you go. Now we can accept jobs. This is one that we'd have to do and accept jobs from. But yeah, so you're over here, you're writing your paper, and you revised it such that your paper length went down. It's like you're a sculptor. You basically vomit, you know, the stone onto the page, and you're just like chiseling a little bit away on the chiseling away the things you don't need until you come out with something that actually looks proper. Which, I'll just add more clay. I mean, you kind of have to. There is a size requirement that you do have to kind of work with, so I mean, and you need a lot more clay, like 3 times as much clay as you currently have. So yeah, so before you arrived, and before the cutscene, I was going over the brief history of object-oriented design.
こんにちは。
I got as far as
今日はどんなご用かしら？
1991, which honestly, most of these dates and most of these people are basically just people that have written books or other on the topics. And then the next major thing that happened was 1994, where you had guys that were previously listed, one of which I had actually mentioned, Booch and Rinbao, who created what is known as the unified model, something that
またいつで
kind
も
of
来てね。
gave way to the Agile Manifesto, which is the process we in the industry referred to as Agile. And it's what a lot of companies that are actually organizing their process use. Helps them keep up with changes to their requirements.
何を作ろうか
It
な。
kind of keeps them on track as well. Nothing gets out of date because everything happens in sprints. It's been a while since I've taken software engineering, so I don't remember exactly every single step of the Agile process, but just know it makes things fast. It does things quickly, in hopes of getting things done quickly, in hopes of getting the product out quickly, and is meant to adapt in case your client decides to not be particularly happy with everything and
これなら
make you
簡単
redo
簡
it.
単。
Okay.
どれを使おう？
Yes, yes, design, very important. You say that. I had mentioned earlier, and I guess I can mention it again. A study done in 2004, which you most important to note is that the client will always tell you to change. Oh, 100%. Because people don't know what the heck they want. They're like, hey, I have a problem. And, you know,
これでいいよ
you,
ね
the developer, is like, okay, what's your problem? They're like, I don't know. Well, it's like, I mean, what am I supposed to do? I don't know your problem. So figure it out. Figure out what my problem is.
どの特性をつけようかな。
TA doing their job. Yes, feel free to add extra details that I don't mention because I am
何を作ろ
very
うか
hard
な。
multitasking right now.
これなら簡単簡単。
But yeah, study in 2004, only 30% of all companies
どれを使おう？
use some form of object-oriented design when they're making their software projects. Me too. Papers being done. Well, at least you only have to listen.
どれを使おう？
Yeah, but the most dominant practice, by some amount, was to not have any practice at all.
どれを使おう？これでいい
To
よ
literally
ね。
just
それじゃあ調合する
be
ね。
handed the
ど
problem,
の特性を
if
つけよ
even
う
at
か
all,
な。
and just kind of just basically running around with it.
何を作ろうかな。
One is inefficient. 2, sometimes it works. 3, most of the time it doesn't work. So, and then in 1995, 3 guys got together, and they wanted to focus on creating a method of kind of diagramming this process of object-oriented design, and they designed what is now known as the Unified Modeling Language, or UML, which consists of a series of diagrams that helps you illustrate kind of what the product is supposed to look like, and basically everything about it. Everything except for exactly its implementation. Which, our professor is really big on whiteboard work, where all the guys would get together and basically map out these diagrams on a whiteboard, kind of figuring out the details as they go, discussing all the things that are particularly difficult, which we'll get to that part a little bit later. That's kind of how we got to UML. UML now being the primary tool for those who are working with the object-oriented design patterns. Okay, my TA is here, so I can now actually begin what the heck object-oriented design is, which I did mention when it was kind of a little bit earlier, but it all really comes down to how you represent your data. When you consider an application,
こんにちは。今日はどんなご用かしら。
when you consider an application that has, as my, yes, this is actually called UML as a sketch, which is heavily implied in agile environments. Yes, it is. Which, UML, if you're working in agile especially, you cannot avoid it. You have to do UML diagrams, of which there are plenty.
これくらいなら楽勝でしょ。
So as my database professor likes to say, and by which I said he lectured us on the first day, a program really does consist of 4 major components, one of which being the front end, what the user, the end user, actually sees and interacts with, the back end, which communicates between the front end and your data, which is the third major part, the database. So everything kind of does revolve around data. Without your data, the backend has nothing to work on, and there's nothing you can really do for your end user, because everything revolves around data. Fourth one is user experience, but we don't worry about that one right now. We're mostly just worried about getting the project that works.
これくらいなら楽勝でしょうね。
So everything revolves around data, but it matters also how you represent that data. How the entities that exist within your problem domain, which are given to you by the requirements that hopefully your client gave you.
お疲れ様。
Turning those requirements into actual tangible concepts that you can work with and that you can figure out how they interact with each other to actually make the system work.
これくらいな。
Which, as far as considering these entities as objects,
お疲れ様。
rather than just abstract data that you just randomly string together and consider a single entity, we have the concept of objects. Go figure. Which, implementation-wise,
これくらい
again,
なら楽勝でしょうね。
the software engineering side of things doesn't really worry about how things are implemented during this kind of analysis and design time. So say we
お疲れ
have
様。はい、これが報
a
酬。
car. A car is something that we see a lot of every day. It's a fairly simple thing to imagine. You don't even have to imagine, you probably just look outside and somebody in your parking lot has a car. So how do we turn this car into an object?
またいつだ。
Not like a physical object, a conceptual object, but... So, we have to kind of consider the attributes of this car, and we have to consider the functions of this car. So basically, what differentiates each car, what data is associated with each car, and what does the car do? What's its functionality? So things that you might associate with your car, for example, the license plate number. It's probably a bad thing to start with, but it is a thing that is unique to the particular car, unique to you, the person who owns the car. That we can just represent as a string of some combination of characters and numbers. Each state has their own
何を作ろうかな。
specifications as to how long it has to be or its format or whatnot. Over here it's like 7 characters, and it's like the first 3 have to be the first 4 have to be letters and the last 3 have to be numbers or
これ
something
な
like
ら
that.
簡単簡単。
I don't remember exactly, it's not important. Another thing you might associate with your car is the model, the make and model. So for example, your Dang, my lack of knowledge in cars is showing.
どれを使おう
Quick, tell me a model of the car. Mr. TA, tell me a model of the car.
どれを使おうこれでいい
I
よ
can't
ね
think of a car that isn't mine.
それじゃあできたどの特性をつけようかな
A Corvette. No, I mean, I was hoping to find one that had like a brand. It's fine. So say you have your a component you would an attribute you would associate with your car to become part of this object would be the model. For example, a Corvette. So you have a Corvette with license plate number that we haven't specified. You know, we mentioned Corvette. It also your car also has a color. That's another one of its
何
attributes.
を作ろうかな
So you're kind of forming this object using all of these attributes. There are also methods that are associated with it. For example, drive. Ford Chevy GT 2500. Welcome, Terra Striker. You have come at an excellent time. We are just now beginning our lecture on object-oriented design in software development. So yes, you have a Ford Chevy GT 2500. Cars are so weird. There's so many weird names for cars. So you've kind of taken the attributes that you associated with this car, blue Corvette, and that is basically how you would define an object. You have this car, this thing that exists physically that you're transferring into a conceptual object to use in your design, and you've managed to turn it into this class, so to speak. And the terminology I'm probably not using it perfectly, but it's fine. So say in your project, if you need to instantiate several instances of cars, so say for example you have an application that registers cars to people, to license plates, to whatnot. So your system would need to have a list, some kind of data structure to represent all of these cars that you have in your database. So instead of having, for example, just I don't know, every 5 rows you have all of the data associated with a particular car. Now instead you can instantiate a single instance of this car object that we have created.
そうだクーデリアちゃんが
Yeah, so you would take all these instances, and it effectively makes your code base simpler, two significantly easier to understand. Because one thing that is true is that most people aren't going to understand what 50 lines of code that are representing this car is supposed to mean, but they are going to understand if they see
今
the
のモ
word
ロナちゃんに
car.
はこれくらいがちょうどいいかもしれないわね
This is just one of the ways that we attempt to make this process easier for ourselves while we're developing this application.
お疲れ様
Alright, any questions? If you ask me what object-oriented design is, I'm gonna slap somebody.
これくらいな
Okay, he's still finishing his paper.
お疲れ様
Okay, so we've kind of figured out, roughly, how we're going to represent
またいつ
these entities in our system. So for this previous example, we've represented these cars that we're working with as a single object with the following attributes, you know, the color, the make, the model, the license plate number, all the data we need with that, and it's all encapsulated in this single concept we call a car. With rectangles. Yes, with rectangles. So now we'll do a little bit more of a concrete example. I say concrete, but I don't exactly have the ability to show you the images that I'm seeing right now, but it's fine. This is all abstract anyways, and all of this is fairly informal. So consider a dice game. A game of 2 dice. So a player playing this game will roll 2 dice. If the total roll is a 7 when you add up the two faces, the player wins. Message retracted. What the heck are you trying to say? Alright. So consider this dice game.
多分大丈夫だね。
So what do we have to think about when we're trying to make this very simple dice game? Well, one of those things we have to consider are... You're trying to draw everything. You'll have to consult the ASCII table for that one. So we have to define things called use cases, which in and of themselves are entire concepts, but we're not so much worried about that as the fact that basically it's a single kind of run from start to finish of your application, what you expect it to do. So for example, in this dice game, we expect for the player, whoever it is, to be able to
何を作ろうかな。
one, play the dice game. It sounds very self-explanatory, but it is actually something that does need to be implemented. You literally have to implement something that starts the dice game. So from there, the player, if they want to roll, they need to request the system to roll the dice. Obviously, the player can't roll virtual dice on their own, so several lines of code are going to need to do that for them. In addition, the system has to be able to tell the player the results. Because obviously rolling the dice doesn't mean anything because they can't see the dice, so they don't know what the results are going to be and they don't know if they've won.
これなら簡単簡単。
So these are kind of the things that our game needs to consider. And how do we turn this into an
どれを
object-oriented
使おう。
model, so to speak?
どれを使おう。
So
どれを使
again,
おう。
we have everything
これでいい
in
よね。
this particular game.
それじゃ
We need to convert it into an
情報
we need to convert them into objects. These kinds of
どの特性を
encapsulations
つけよう
of
か
data
な。
and functionality that will basically dictate our general design. So
何を
on
作
here
ろう
it has a
かな。
domain model, of which I can't show you, because obviously I can't show you a domain model. But we have identified our objects in this particular game, one of which being the player, of course. The player needs to obviously know when they've won the game. If there's any data associated with them, for example, the number of wins they've had, the number of losses they had, things, or their name, we can associate all that stuff with them as well.
これなら簡単簡単。
Otherwise, it's not quite that complicated for the player. Another object we need to consider is the dice game
何を
itself.
作ろうかな。
The actual mechanism by which we can play the game. So for, in like real life terms, if you were trying to play the game of Monopoly, something you like actually physically need in front of you is the game of Monopoly. So that's kind of what the dice game here as an object represents. After that, you have, of course, the dice. The things that that the player is actually rolling, and their only means by which to win or lose the game. So now we have 3 objects that are interconnected
どれを使おう。
in some way.
これでいい。それじゃ調合するよ。
So a player object will need to roll 2 dice. So that is a connection between our player and our dice. Oh, evaluation day. Okay. 5-minute break.
今回の依頼も無事に終わらせたようだな。
Feel free to grab a drink. I need a drink.
無事かどうかまだちょっとわからないですけど。
そうだったな。では早速それを確認するとしよう。
Alright, we completed it. We'll be right back after this commercial break. By commercial break, I mean like the actual literal gameplay break.
いいんですか？こんなに高い評価で。
I mean, isn't that kind of how the Super Bowl works? Now that I think about it, because one of the greatest things about the Super Bowl for like American football is, well, are the commercials. The commercials are like, for most of us that don't particularly care about football, that's what we watch the Super Bowl for. So honestly, the actual gameplay coming up really is a commercial break for us. that's all we care about. I might honestly take some notes on this stuff. It seems interesting. It does require some fundamental knowledge of computer science, but really the bare minimum. It's a design process. It's something that really mostly applies to the digital space, but it doesn't necessarily have to. Because whether it's a house or whether it's a video game, all of it is simply the sum of its components. And the object-oriented design basically helps us organize those components. So you can kind of extend it however you will into whatever you need it to be. I'm in cybersecurity class right now. I just know this. Okay, that's good. That's good. Which, fortunately, there isn't any code in here, so you don't have to know like Java or anything. But yes, object-oriented design is kind of the basis for a majority of organized projects.
ああ、錬金術についてはよくわからないが、おそらく十分だろうとの判断らしい。
And in case you're curious about this information, it's all coming from exactly what I learned today. Like literally, I went to class today, and I'm just spitting back out everything I learned. I tried and failed to learn Java. It's fine. Though I do recommend trying to go back and learn Java. Like, try and start as basic as possible. Because if you know Java, then, well, my professor always says learn C++, but C++ is a little bit harder than Java. But just try to keep it simple as much as possible when you're learning something like a coding language. It's like learning a real language. You start with the alphabet, and you just kind of learn words as you go. Learning programming languages is much the same.
なんかおそらくとからしいとかあんまり褒められてないような。
確かに曖昧な表現が多いな。
If there's demand for it, maybe I'll do a Java tutorial. It's not going to be a good one, but it does. You will have. You should solve the halting. No, TA, don't make him touch the halting problem. No, bad TA.
だが、今後の君の活躍によっては、この評価が間違ってなかったことが証明されるだろう。
Nothing. Okay, so if you're curious about the halting problem, I'll ask you this. Do you think it is possible to write a program that could detect if another program will loop indefinitely?
そうなるといいんですけど。
Just a yes or no answer. Do you think it's possible?
そうなることを期待している。では、次の依頼の話に移るとしよう。
Turn in meals for the annual festival. You're evaluated on amount of quality. Yes, I think so. Okay. So the halting problem was kind of created to answer this particular question, which is to say you have a loop, you have a while loop, and say you have the while loop iterates some number of times. So it's literally while true loop, and somewhere along the way there's a break statement in there to exit the loop. How do you know if the loop is going to terminate? Because the thing about the code is that when you're evaluating a particular program, especially something that is user-facing, you're never entirely sure if or when it will ever end. So consider the program runs 10,000 times. It's like it's looping 10,000 times. Do you think it will loop indefinitely? But say you do think it's like, okay, let's say 10,000 it is looping indefinitely. Well, but what if the 10,001th iteration of the loop, 10,001st iteration of the loop, it terminates? And you accidentally killed it too early because you thought it was going to loop indefinitely. Or you're like, okay, it shouldn't loop indefinitely, and you let it run. And it runs for, 10 to the power of like 17. Not if there's a break somewhere in the code, not necessarily, because a break existing in the code and a path of execution such that it reaches that break statement isn't always guaranteed. For example, if you have a while loop, and you have inside the while loop an if statement that says if some value, say for example some user inputted value, equals 1, right? So you have an if statement, right? It's like if-else statements. So if the first statement is true, it runs the first block. If the else statement, or if the if statement is false, it runs the else statement. So basically, say if x equals 1, then you break. Else, you just continue looping. So if we consider that this is a user inputted value, if the user just never inputs x as 1, then no matter how many times the loop runs, as long as you don't input 1, that loop is never ending.
王国祭の準備ですか。
そうだ。日程の都合上、期日がいつもより早くなるので注意してほしい。
That's the thing. Whenever the human gets involved, then just looking at the code sometimes isn't enough. Or even if the human isn't involved and it's just a particularly complex math problem that just needs to continue calculating over and over and over again. But it never actually reaches its point of execution. That's like, if it's not just as simple as iterating I plus plus while I is less than 10, it's not, a lot of times when you're looping, it's not usually that simple, like pi. Well, if you set it properly, then as long as if you're iterating I to some value less than or equal to pi, then after a certain number of iterations, you'll be greater than pi, and then it'll exit. But basically, the halting problem has stated that you can never figure out whether it is looping infinitely or if you just haven't reached the end of execution yet. So that's why he told you to solve the halting problem, because it is physically unsolvable.
もうそんな季節なんですね。今年に入ってからずっと忙しくてすっかり忘れてました。
Yeah, so if anybody ever gotta finish his homework, TA out. Alright, have fun, TA. So yeah, if you're ever asked if it's possible to determine if something will loop indefinitely, the technical answer is no. The technical answer is no, it is not possible. In very simple cases, yes, you could just read the code, but otherwise there is no generic solution that you could program into an algorithm to just check in every case whether or not something will loop indefinitely. That's the halting problem.
そうか。すまない。君のような年頃の少女が多忙に追われているというのは好ましい状況ではないのだが。
Because the problem doesn't care about situations where you can just look at the code as a human and just figure it out, because, well, that's something we can do better than computers just sometimes, But it's the process of creating an algorithm that can do it for us that is impossible.
いえ、そんなつもりで言ったんじゃ。大丈夫ですよ。お仕事だってちゃんとそれなりに楽しんでますから。
それならいいのだが、城の方では王国祭の催しをいろいろと考えている。依頼を終わらせたら、君もぜひ祭りを楽しんでほしい。
You'd have to program the entire workings of the memory of the human into the computer. I mean, the whole brain, basically. I mean, I guess theoretically, if you put an entire human into the computer, the human can just eyeball it and figure it out, but we haven't done that yet.
はい、楽しみにしてます。
Which we've scanned an entire brain into a computer before, but we can't make it sentient. There was somebody at one point in time that basically donated their brain to science, and they like froze the brain and like shaved these like really minuscule sheets and scanned them in, and basically had a whole model of this guy's brain. So there's research. That's like type 3 civilization. We have names for things that don't exist. You know, for of course.
残念だったな。せっかく遊びに来たのに仕事で相手にしてもらえんとは。
The cutscenes will end soon. We just have to get through the first bit after the start of the assignments.
別に遊びに来たわけじゃないわよ。暇だからブラッと寄ってみただけで。
暇だからね。
何ニヤニヤしてんのよ、気持ち悪い。そうだ、いい機会だし、あんたに聞きたいことがあるんだけど。
私に？なんだ？
あんたさ、なんでロロナを弟子にしたわけ？
可愛いから。
一応真面目に聞いてるんだけど。
真面目に答えてるぞ。少なくとも 60% はそれが理由だ。
じゃあ残りの 40% は？
バカだから。
真面目に聞いてるって言ってんでしょ。
だから真面目に答えているじゃないか。バカという単語が気に食わないなら才能と言い換えてもいいぞ。陳腐な表現だがな。
なんでバカが才能なのよ。
そうだな、どう説明したものか。例えばここに猿でもわかる魔法の唱え方という本があるとしよ
う。何よそのタイトルは。
だから例えばだ。でそれを読んだらクーちゃんは魔法が唱えられると思うか？
クーちゃん言うな。そりゃ唱えられるんじゃないの？猿でもわかるんだし。
本当にそう思うか？
まあ実際にそんな本があっても信じないでしょうね。
そう、中途半端に頭がいい人間はまず疑ってしまう。それが問題だ。天才なら一瞬で理解するし、バカなら何も考えずに試してみるだろうからな。
つまり錬金術は天才かバカしか使えないってこと？
それは違う。錬金術は学問だからな。ちゃんと学べば誰にでも使える。ただ頭のいいやつには一から教えてやらないといけないが、バカには教える必要がない。
わかるようなわからないような話ね。要するにロロナはいい意味でバカってことでいいのかしら？
Interesting analogy. Yeah, see, this is actually really related to our topic. It doesn't look like it, but if you squint enough, we're basically, us and the game are basically talking about the same thing.
ああ、天然で純粋無垢なバカだ。あれほどのバカはそうはいないぞ。
Which a lot of the biggest breakthroughs in like maths and sciences have been by people that their brains literally make absolutely no sense.
なんかすごいバカって言葉が聞こえてくるんだけど、もしかして私のこと？
Okay. Oh wait. I'm just completing quests and I haven't done anything yet. Okay. Where was I? Oh yes, the dice game. We were at the dice game. So we turned every single entity in this dice game into an object. But we haven't exactly elaborated on the data associated with each one of these objects that we've created. So for example, well, we have mentioned some things about the player. The player, of course, will have a name. They might have a win-loss ratio, something that our game can choose to keep track of if we felt like it. Other than that, dice game might have like a whole lot of state information that we don't really need to care about for this particular example. But something like dice, or the die, in this case, the single object of the die. The die will have the face value, So for example, whatever the roll is, say if we feel like storing that in the instance of the dice, then we can. Other than that, that's basically all the data that we're concerned with at the moment. But the thing about objects is that they encapsulate not only the data associated with those entities, but also the functionality associated with those entities. So if we consider something like the dice, we might extend our current definition of the dice to include a method. Methods being effectively function calls that occur inside an instance of an object to do stuff with the data either given to it and available to the object that it inherently knows about itself. So for the dice, we'll have face value, which is an integer. So every method that we call to this dice object, it will always have that face value visible to it. It'll always be able to use it in its calculations as such. So one of the methods that we would implement in this case would be a roll function. Something that, runs a random number generator from 1 to 6 inclusive that returns the number, the number that was rolled. So whether we choose to do this once or twice, that's decided by the design, but the example it does have on here instantiates two instances of dice. So you have die 1 and die 2. And for each instance of die 1, when the player chooses to roll the dice, you would roll the dice. So if we're following the general kind of happy path of use cases, here we would kind of consider from the very beginning, the player opens up the game, this player object is created, stores all the data of this player. Say we tell the user to enter their name. They enter their name, it gets saved to this instance of this player. And now the player will, say, press a button on our graphic user interface that says start the game. They start the game, and now the dice game object is going to call. Well, before it calls, it will instantiate. So given this kind of blueprint of a dice we created, it'll create two instances of this dice. And using that, we now have two dice. Conceptually. Conceptually, we have two dice that have been created, and for each dice, we are going to call their relevant roll function. So this roll function is going to, of course, roll the dice and return to us the value, the face value. So with that, now the dice game has access to both the die rolls and access to the player, so now it has everything it needs to determine whether the player has won or lost based on the rolls. And that's basically the general format of these this dice game. So we identified the objects, the entities that our application needed to consider. We found the associated data to each of those entities and their general functions. And then at the end, you tie it all together to create a working application through, I don't know, coding in Java or C++ or something. Again, as far as the design process is concerned, which it's... Oh wait, so the dice game itself also has its own data on the rules and stuff, right? Yes. So the dice game, of course, will need to know. The dice game object, either inherently or by some other means, will know what the roles need to be in order for the player to win. Which in this case, you could, at the very least, break it down to, say, an add function. Given die 1 and die 2, add their face values together. If equal to 7, tell player they won. But yes, the dice game is its own instance of an object. So, As far as the system is concerned, just consider everything as an object. Like even like the you could consider the graphical interface as its own kind of object, but that's a whole other thing. So in the textbook and in the notes that I'm using, there are a lot of diagrams of which I cannot show any of them, but it's fine. I'm sure you can kind of get the general gist of how we break the game down into its components, so to speak. Like I said, everything is the sum of its components. Alright, let's see. Unified modeling language. A lot of this stuff is... I mean, if you ever have the chance to actually, like, look at a class diagram or a design class diagram or a domain model, like UML model, for all these things, you can always look at it. It'll probably give you a good idea of what visually some of these are supposed to look like. Alright. Where was I? Yes, applying UML. Because again, a lot of the reason why we have object-oriented design, UML, all this stuff is to make our job as developers easier. And there are a handful of ways of how we go about this. How we kind of take these diagrams made using UML to help us. So one is to apply UML, the Unified Modeling Language, all these little funny diagrams, is to apply them as a sketch. So this was, as I mentioned a little bit earlier, but I don't know if you were here for it, my professor is really big on a bunch of dudes standing around the whiteboard actually drawing these models and discussing them as they go. Which is kind of similar to how the Agile process does it, where it's, the Scrum team would get together and basically figure out this stuff. So when you use UML as a sketch, the diagrams are a little bit more informal. You're not trying to highlight literally everything about the objects. More so as you're trying to basically figure out the difficult stuff. What needs to be broken down the most, how you would solve X problem that eventually you will implement to get working. But with using UML as a sketch, you're definitely less concerned with the kind of more trivial bits. Trivial kind of depending on the project, but at like a really high level, for example, like a sorting algorithm. You could easily just Google a sorting algorithm online, and you'll find one that's mathematically proven to do its job perfectly. That's basically one of those trivial things that you don't really need to highlight very much. So using UML as a sketch, you're kind of only considering the major pieces, the things that are going to stump you at literally any point across the road. Let's see. There's also UML as a blueprint, which is the kind of more formal option. And it's exactly what it sounds like. You're using your UML diagrams to create an exact blueprint of what things need to look like. Which hopefully does take a little bit longer, but it does have the benefits in that using these blueprints you created with UML, you can kind of figure out the code itself. Because a really good UML diagram can, with some tools, give you basically the skeleton for the actual program you're trying to write. Which, you know, nothing beats writing it yourself, but the one thing that's constant and no matter what you do is that deadlines are always approaching. So time saves are always important. What else? UML as a programming language is basically an extension of that, where it's literally exactly what it sounds like. Yeah, you're using UML to basically generate all of the code for you, but this one's not very used. not used very often. So it's not something we're really considering all that much. Alright, our perspectives for applying UML. Which, the UML part is kind of static, where everything is under the assumption that we are using UML. We can do it conceptually. Kind of, as we were doing earlier, turn real-world objects into these kind of things, these concepts that are important towards our particular problem. Specification. Applying UML for specification. It can help you kind of organize the interactions between all of your particular components. For example, in the dice game, the player had to interact with the dice game to interact with the dice. That kind of figuring out that order of events is part of this design process and part of what UML is supposed to help you for. Implementation, very obvious. UML at the end of its day is meant to help you with implementation. How you implement it isn't amazingly important for the design process, but it is something that you will eventually need to deal with, so making your life as easy as possible on that end is always a benefit. Which, funny thing is, like, no matter what process you use, there's something referred to as the 80-20 rule, which states that 80% of the work in completing a project is done in the last 20% of that project's scope. Basically, the last 20% of features is where 80% of your work is put into. And that's almost not an exaggeration. So yeah. Visual modeling, we're not worried about. History, we kind of already went over with, that's kind of dry. Okay, I don't know if I already mentioned this while you're here, but... Oh yeah, I get that a lot, yeah. Like, I've worked on some projects, especially ones that, for obvious reasons, never finished. But, like, at the very beginning, it's so easy, and then after a certain point, you're just kind of stuck. A study in 2004 discovered that even though object-oriented design has been theorized since, what, 1967, and has kind of been shown over the years to make things significantly easier, only 30% of projects that were studied actually used object-oriented techniques. Because of burnout, yeah. In a lot of cases, it's just school, work, all those little things. But the most dominant practice of all these projects was to have no design at all. Was to not use any kind of technique. And I forgot what it was called, but basically just immediately getting your problem and just immediately start writing code, which in most cases you want to avoid. Who the heck is this kid?
よう、あんたが新しいアトリエの店主か？
そうだけど、君は誰？ダメだよ、勝手に入ってきちゃ。
頼りなさそうな顔してんな。大丈夫なのか？あんたみたいなのが店主でさ。
それは全然大丈夫じゃないけど。でも師匠が無理やり。
まあ、そいつはどうでもいいや。俺はコール、行商人なんだ。わざわざ来てやったんだから、何か買ってくれよ。
Oh, this kid's a merchant.
行商人？子供なのに？
中身は姉ちゃんよりよっぽど大人だぜ。それよりほら、見てくれよ。
どれどれ？見たことない材料がいっぱい。
へへん。独自のルートで仕入れてるからな。
当然だ。生意気で可愛げのない男のガキに金を払うほど水教ではない。
わあ、師匠いたんですか？
はっ、 こっちだって金を払わない客に愛想振りまくほど暇じゃねえんだよ。
店が客を選ぶのではなく、客が店を選ぶんだ。商売人の端くれなら覚えておくんだな。
喧嘩はダメですよ。
で、どうだ、姉ちゃん何か買ってくれるか？よあ、今日もいろいろ持って
Oh, he literally just has a shop. Okay. Yeah, so
ど
back
れが
to
欲しいんだ？
the lecture, we have a lot of what are referred to as design principles. These kind of things that have kind of been made to solve consistently appearing problems. So things that a lot of people, as they're developing, have kind of come up with and have found a reasonable solution for that works for basically every instance of the case.
もういいのか？ 毎度あり。またちょくちょく寄らせてもらうから。あ、待って。なんだよ。コールくん。コール。一文字略しただけじゃねえか。普通に呼べよ。じゃあな。
どうだ、生意気なガキだろ。
そうですね。可愛い呼び方だと思ったんだけどな。
On the 15th of every month. So yeah, so every kind of methodology does have its own design principles associated with it. So what was commonly used before object-oriented design, which is what you'll see in a lot of early languages, is functional decomposition. It's where you'd basically take a really big problem and break it down into its relevant functions. It improves readability. It generally just does make a lot of things significantly easier to understand. However, it doesn't quite abstract things as well as object-oriented does. There's a whole thing, like Mr. TA is currently working on a paper on the differences, and I'll have to deal with that paper eventually as well, but... let's see. Yeah, managing intellectual complexity means solving ever more complex problems, and to solve ever more complex problems, you have to simplify the problems as best as you can. So for functional decomposition, the most common design principles that we're working with here are divide and conquer. It has a lot of other names for it, but I've never seen them, so I doubt you'd have seen them, so we're just going to refer to it as divide and conquer for now. Basically, quite literally taking advantage of parallelism. Or even if not parallelism, just, I forgot the term, but divide and conquer is fairly self-explanatory. Usually if you are dividing and conquering, it's it's recursive, which isn't fun, if you've ever worked with recursion. Separation of concerns. Basically, you want each function to only be concerned with one thing, so while you're working within your kind of main operation. Random unrelated question. Do you and 2A know each other in person? Yes, we are literally in the same class for this topic. Dang it, still not enough. So yeah, so we have the same homework assignment, and I was basically just giving him background noise of this particular assignment to kind of not really help him focus, but to just kind of like to literally give him something to listen to. Functional design composition, modularity. Break the system into modules. Fairly self-explanatory. So, for example, if you have a list of things that occasionally you need to have sorted, rewriting the sorting code at every instance of your program that you need to be sorted is wasteful, for one. So you'd break up the system into your kind of main, and then these external functions that you just need them to work, and you need them to return what you need them to return. So creating two separate modules, basically. One being your main, the other one being the function that your main will call when it needs to, at every instance that it needs to. Module size. Oh, there's something funny on here. Just out of curiosity, how many things at once do you think a person can understand at once? Like, just give me a number. Like, if you wanted to... If you say you could perfectly understand some n number of things simultaneously, how many do you think you'd be able to understand at once? It's kind of an odd question. Maybe like 5. Yeah, basically. So Miller's law states that a person can at most, maximum, understand 7 plus or minus 2. 7 plus or minus 2 things, which the number keeps going down as you age, but it's not many things. So when you're working on a project that's, 3 million lines long, trying to remember every single feature of within those 3 million lines is impossible for one. So figuring out the size of your modules is important. So some people like to say your functions should fit on, no more than a page, right? Or 2 pages, so to speak. Or some are like, okay, maybe your functions need to only be like 5 lines. Really is just kind of at discretion, but you don't want your methods to do too many things. Because if your functions are doing too many things, then they become more difficult to understand. So you do want to manage the size of these modules that you've created. Let's see. Structure design. Oh, I guess that is another set of design principles. The ones that a lot of which we use in object-oriented design. One is being information hiding. Hiding the things that your other functions don't need to see. Also things that are more than likely going to change. So for example, if we consider back to the sorting, the program that needs to perform sorting every once in a while, you want to decouple as much as possible the functionality that happens in your main and the stuff that happens in the sorting function. As far as main is concerned, the sorting function should basically just be a black box. You either just throw something in and something gets spit back out at you. It's because say you have to sort 15 times during your program. So that means if you don't turn into a function, you have 15 different instances of the same code in 15 different places across your program. So that means, say if at the beginning you implemented a bubble sort, which is a particular method of sorting that's n squared time to complete, and later you decide, okay, let me do a quick sort instead. That one's faster, it completes in big O of n log n, which is faster. So if you decide that change, then you'll have to go back to all 15 instances of that sorting algorithm in your program, which, in a large program with, 3 million lines, they could each be several hundreds of thousand lines apart. So trying to make those changes is expensive, time-consuming, and overall just not worth it. So that's information hiding. Hide the things that you think are going to change. Even if you don't think they're going to change, if it's possible to hide them, you should. Just in case, because again, the fundamental rule of software development is that requirements are always changing. Your client can just walk up and say, oh yeah, you know everything I told you earlier?
一応
None of that is relevant anymore. Do this instead. So, in those cases, having all of these black boxes basically helps changing your implementation to be a whole lot easier. Because again, as your requirements change, your design has to change, and therefore your implementation has to change. So you want to make those changes as easy to perform as possible. And with that we get to abstraction. Extraction and encapsulation, which, as kind of bare minimum definition, it's basically encapsulation is basically information hiding. You have your object that you created, for example your class, and you're considering that as kind of like a little capsule, and you're putting everything relevant to that object inside that capsule. Nothing else needs to care about it unless they open that capsule and look at it. So your other methods aren't running around with unnecessary data, they're not calling unnecessary things. And again, it keeps things organized. And it also protects your data. So if this data if the data required for the dice, for example, is to roll the dice, so the random number generator, if that's completely unique to the dice, only the dice ever needs to look at it, then the player should never have access to the random number generator inside of it. So you're encapsulating that random number generator functionality inside this dice object to protect basically your dice. Abstraction. Hold on. Yes, abstraction is basically to provide only the data that a particular function or object needs, which encapsulation and abstraction sound pretty darn similar, and in practice they're basically going to be doing exactly the same thing, but they're technically two different terms. Though this doesn't count abstract data types, because that's a whole nother thing. So, for example, if you have a sorting function, it needs the list that it's sorting, obviously. So say if your function also has... say your function has 3 lists of 3 different things, all of which may or may not need to be sorted at some point, doesn't really matter. Say you only want one of them at any particular time to be sorted. That means your sort function doesn't need access to all three lists. It only needs access to the one that it is actively attempting to sort. That's abstraction.
どれを使おうかな。これで壊せるかな。
Information hiding. Okay, this is like straight from the textbook. Information hiding principle is the principle of segregation of the design decisions in a computer program that are most likely to change, thus protecting other parts of the program from extensive modification. I forgot where I was. If the design decision is changed. So you would basically create a kind of interface between your module and your other module of data. So for example, if you're trying to sort the list, I always go back to the list sorting because it's easy, then the sorting function needs to be given the list, and the only thing it needs to give back is the sorted list. Nothing else about its implementation really, the other module does not care. So it does not need to know, and it shouldn't know. That's one of the concepts where you make your components as dumb as possible. They literally don't know more than what you tell them. We can skip the part on abstraction, encapsulation. I think that's a good spot for object-oriented programming. Any questions? That's as far as we got in lecture today. Yeah, any questions before we move on to the machine learning part?
何を作ろうかな。
How do you actually separate the data? Okay, so do you know what a class is? Or do you know what a function is? Do you know what either of those things are? Okay, so a function, yeah, so how do you actually separate the data? Okay, so do you remember how we had, for the dice game, 3 different objects? We had one for the player, we had one for the dice, and we had one for the dice game. So we know the player contains all information about the player. Their name, their win-loss ratio, etc. The dice has its face value and has a method to roll. So if we consider the general running of this game, the dice game will have access to the dice and the player. But, so where the separation occurs is that the player has their own functionality. They have their own data associated with them, and the dice has their own data and its own functionality associated with it. But the player doesn't know what the number on the dice is. And it also doesn't know how to roll the dice. Just like how the dice, the instance of the dice that you create, doesn't actually know anything about the player. It doesn't know the player's name, it doesn't know the player's win-loss ratio, it really doesn't care. So we've kind of separated these 2 different entities' data into 2 separate objects that interact independently of each other. If the program didn't need the dice, then you'd literally have no dice created and the data wouldn't exist at all. So the class, a class in programming, in a language that supports object-oriented programming, is basically an entity that has attributes. So for example, it has integers, strings, floats, etc. And it has functions inside of it. So for example, if we were defining the car, for example, it would have an integer for, I don't know how many miles it has. It would have a string for its license plate number. All of these things would be defined inside the class declaration. Like, I can't show you syntax, but that's basically how it works. So you know how normally you would define variables in a functional decompositional way. It's just at the top of the program. At the top of the page, you would just define all these variables and you would just use them. But with a class, you define it inside the class, and you also define a function inside the class, instead of just anywhere on the document. So now this functionality and these attributes are limited only to the class. Only this class can see it. So only this car can see its own attributes. Only this car, for now, can call its own functions. So you connect it to your existing program. For example, if you have a program that registers people for cars, you might open up one of those functions in the car object, and the car management program does not care how the car registers. It's like, you know, how the car changes its license plate number. It doesn't really care about that. All it needs to know is that if the car management program wants to change the license plate of this car, it just sends it just basically calls a function in the car and says, hey, change your license plate number. I don't care how you do it, just change it. So the kind of what happens in between is completely separated between these 2 objects, between these 2 classes. So that's kind of how this data gets separated, except on like a significantly larger scale. Any other questions? Nothing good. All right, so we can move now on to the machine learning side of this lecture. I was hoping we'd also get to the database stuff, but that's going to have to be a lecture for another day. All right, let me flip some pages. By some pages, I mean a lot of pages. Because these ones are in the front of my notebook. Always gotta take notes in class. Alright. So last time we did kind of go over supervised, unsupervised, and whatever the third one was. I keep forgetting what. Reinforcement learning. So the lecture that we got today focuses on supervised learning, which, as far as we're concerned, is the most important because you can extend supervised learning to any of the other two types. But before I do that, I'm going to read this cutscene.
偉い偉い。今日はよく逃げ出さなかったわね。私だっていつも逃げてるわけじゃ。
つうか、そもそも逃げないのが当たり前なんだけどな。
そうだけど。リオちゃん。あ、見に来てくれてたの？今日はちゃんと見れたよ。リオちゃんかっこよかった。そんなこと。
リオネラだけか？主演男優を目の前にしてそりゃねえだろ。
ごめんごめん。ホロくんもラニャちゃんも素敵だったよ。お褒めに預かり光栄ですわ。そうそう、それでね、ラニャちゃんとホロくんって喋るだけじゃなくて自分で動けたりするの？
んなわけねえだろ。自分で動けたらリオネラいらねえじゃねえか。
そっか。じゃあどうやって動かしてるの？糸とか全然見えなかったし。あ、その糸は見えない糸で。見えない糸。すごい。どんな糸なの？見せて見せて。見えない糸を見せてって言われても、確かに。
しかもこいつはただの見えない糸じゃねえ。バカには見えない糸だからな。
じゃあ私バカってこと？
Yes.
違うの。嘘。全部嘘なの。嘘？じゃあ私バカじゃないの？違う。嘘なのはそこじゃなくて。じゃあやっぱりバカなんだ。だから
なんか一生やってそうだな。
あなたが余計なこと言うからでしょ。まあリオネラがこんなに喋るのは珍しいし、しばらくほっときましょうか。
Okay, this next part is a lot of math. Alright, where to start? So, as we've kind of gone over supervised learning, you provide to the machine, with each sample, everything it needs to know. Oh, yes, show me those invisible. I mean, it's probably the case of like, oh yeah, the strings are invisible, I'm just hiding them from you. But, I mean, I guess in this case it's literally just like, woo, magic hands. They said literally just cast mage hand, I guess. So yeah, so supervised, you provide with your dataset to the machine, the label, as we call it. So what the,
Yo, oh my god.
if you're trying to teach the machine how to detect whether a person is going to have a heart attack I don't know, for example, you would provide them the features of this person, which are basically the inputs. So for example, their blood pressure, their I don't know, BMI. We'll stick with those two for now. Their blood pressure and their BMI. We'll consider those two items as features for this for an entity in this dataset. And while giving them that, you're also telling the machine whether each person in this dataset has a heart attack. Yeah, because we're trying to figure out if they have a heart attack. So that's supervised. Unsupervised, if you recall, is you give them the features, but you just don't tell them if they had a heart attack or not. So with supervised, it's a bit of a process. Where's the cookie? Yeah, so given some training example, x, we have to use x, such that implies some y value, where y equals f of x. You want your system to basically guess what the next closest function. So the function that defines the relation between these features that we've given at this machine and whether or not this person has a heart attack, we don't know. Just nature decided that or whatnot. So, but we want the machine, given all this data, to get as close to that as possible. And kind of to that end, you start by giving it training. You basically give it training points. So some XY pair. So given the inputs of X, which are, blood pressure, BMI, and Y, which is the result. Did the person have a heart attack or did they not? Given these particular things, we're going to teach the system basically the relationship, and we want it to predict what that relationship is and get as close to the natural f as possible. So it's going to learn given these training points, and it's going to give you some function g, we're going to call it. G is its closest prediction to the natural function f, which is the exact relation between these inputs and the heart attack. So from this g, we give the machine test points. So instances that we draw that the machine didn't have access to during training. So completely new points of data. And we hand it to the machine, and the machine predicts the result of these test points in what we're going to call y prime. So using g, by applying g of x, we get y prime. So this is what the machine predicted. And we're going to use those test points, of which we know the actual answer for, so we're going to call those y. And with that, we compute a loss function using y and y prime to determine basically how accurate the system was. How accurate was our training? How well did our machine learn? And we kind of build up from there. Which, if it's really lost, if there's a high loss, basically it wasn't very accurate, and we're going to have to rethink our algorithm, of which we have learned none of yet, so that's fine. So the challenge is that you don't exactly know for sure like what level of loss is okay. if you know if that makes sense. So obviously you use your loss function, you consider what the consequences of a certain level of loss means, and you use that
ど
in
こにスタンプを押そう
to
か
you know either more or less rigorously train your machine to figure out, basically do better at solving the problem each time. Which it's a little bit complicated how you get there, but all that matters is that you use your desired loss to train your machine, of which after you've trained it you give it test points, and using these test points you basically evaluate how close your machine was to the actual real function using those test points. As for how it goes about doing that, one of the ways that we're kind of looking at it is, imagine a graph, if you will, and imagine a sinusoidal curve. So just, for example, sine of 2 pi, or something like that, plus 1, we'll say, as just our function. And you know, that's something that's very easily graphable. If you have a graphing calculator, it's actually possible to graph it. But what it looks like right now doesn't particularly matter. But what we're going to do is
ラインが揃ったようだな
apply what is called Gaussian
では
noise
報酬を渡そう
across, we'll say 9 points across the graph. And so that noise is going to shift each of those points a little bit off of the actual function line to generate 9 seemingly random points on a graph. And what you do is you take away that line that you used to make it, and each of those points, those XY coordinates, we input as our training points.
では引き続
So obviously the machine wasn't given the original function. All it sees are these 9 points that are roughly related to the sinusoidal function. But again, it doesn't know that it was a sinusoidal function.
依頼の品を持ってきた
So what we do is we guess. We basically guess some kind of curve and have it
では
basically attempt to see if it fits. So we do what is called assuming the form of a function. So we're going to assume that these 9 random test points, of which we have no known function for, we assume that there is a function for it. And with that, we restrict our domain to some value that you can only really gain by experience, but for now we'll say it's a polynomial. Polynomials are easy. Literally some value of x to the power of 2 plus some constant x to the power of 1 plus some constant, etc. Polynomials are really easy to look at, really easy to understand, where, you know, the square is just a simple parabola. It's hard to describe a cube function, but I'm sure you can imagine it. So from there, you restrict your domain to this polynomial, and you attempt to fit it to the points, basically. Okay, so the other part of this particular lecture does involve evaluating 3 different types of graphs, but we can't do that. But now that we're assuming that it is the form of a polynomial, and that's kind of how we're going to operate. So we imagine this n-ary polynomial, this n-ary polynomial, meaning it could have the highest power could be any value of n. And we're going to find the weights So the coefficients basically for each of these powers of x's that get us close to the values of that are on this graph. So if you have 9 points on a graph, it is possible to create a polynomial, an n degree polynomial, such that every single line is there on the graph. Which I don't know if you've ever seen anything to a polynomial with a max power of 9, but it's ugly. So that's kind of one way that you could guarantee that at least all of your test points are in your predicted function. So I can't show it, but you could also choose instead 3, which gets you some of the test points, or sorry, the training points. But again, since I can't show you, it's kind of awkward, but one of the things we run into while we're doing this is the potential of overfitting. So for example, if we did this n degree polynomial that that basically hits every single one of these points, there's a good chance that if we add any other points to this polynomial, that it's going to cause a whole lot of mess. Where if you wanted to reevaluate your function, adding say a 10th point, your n degree polynomial graph is going to change drastically. First is a polynomial with lower degree, where if you add just an extra point or two, it maybe just gets a little bit wider, gets a little bit shorter. It's a very small change. So this process of taking in too many training points is called overfitting. So basically we're guessing a function that is way too complex, that basically makes our continual training of this machine significantly harder. So it's one of those, so it can either be caused by, again, our function that we're guessing with being just ridiculously complex, or that we just don't have enough data to actually reach a reasonable test. Okay. So yes, that's overfitting. There's a lot of terminology on here. Where does it go? That's this domain. Okay. So when it comes to learning algorithms, of which again I have none at the moment, they have three major considerations. One is how it performs a search. So whenever you introduce a new training point, the search is basically the means by which it attempts to update its function to reach a closer y prime to y. So one of these ways is direct computation. Basically, every single test input you get, you just immediately calculate what the next one would be. So basically just hard calculate, using all these test points, what the function is, just right there. Another one is to do what's called a local search, which is where you make an assumption, you just select some kind of function that maybe kind of works, and then very gradually, as you get more testing points, you just improve it little by little at a time. Which, in terms of just like a single stream of computation, is going to be a lot simpler. The other way is constructive search, which is to basically say you start with absolutely nothing. You start with no guesses, no function at all, and from each point you basically just start growing your function till eventually you hit some maximum. So that's searching. the next thing is timing. Basically, when does it perform the search? So there are two types, aptly named after people. One is lazy, the other is eager. So eager basically says it analyzes training data immediately and constructs a hypothesis. So basically, you hand it data, and just immediately starts figuring out what the function is. Versus lazy, which is to say, you hand it the training points, but it just doesn't look at them until you assign it test points. Until you assign it something that it has to figure out on its own. Then it uses those training points to figure out what the function is. Which, you're still figuring out what the function is, but it's basically just determining when you do it. That's timing. The third consideration is whether you do it online or batched. Which is kind of self-explanatory. It's online. Basically, the moment you get a training point, you just immediately start calculating it when it arrives. Or versus batch, where you wait until you get a handful of training points, and then you decide, to find the function. So basically doing it one at a time as they arrive, first come, first serve, or to wait until you get a few and start calculating it. So those are the three kind of major considerations for the learning algorithms. Kind of deciding how you're going to implement these algorithms. There are 3 on here, but there's no... we haven't quite gotten to exactly how any of those are implemented yet. Although, hold on, there's another page on linear regression, but... that's a lot of math. Yeah, there's something called linear threshold units, which is complicated. It's the least complicated, but again, it is a lot of math, because you're basically assuming some hypothesis where... Okay, it's very complicated. Okay, we're just going to skip that part. Any questions? And by any questions, did you understand like 5% of that? Like maybe 4%. That's fine. Honestly, the fact that you got at least 4% is is good, because like I said, this stuff is complicated. This stuff is really complicated. And even with visuals, I'm not good at mathing. Neither am I. Like, especially when you're doing linear threshold units, you're working on a 3-dimensional graph with all of your training points on the graph, and you basically have to find a plane that cuts through this 3-dimensional form and separates the points that are positive and the ones that are negative. Basically, did the person have a heart attack or did the person not have a heart attack? And yeah, you're basically drawing a plane in a 3-dimensional space to separate these two these two situations. Which, the moment you get 3-dimensional, graphs involved and, cutting through them with planes, things just get complicated. It's been quite a bit since I've taken stats, so I don't remember how a lot of like the linear regression stuff works as of right now. Which, this is a senior level course for a reason, I guess. Oh, did I not do this yet? Danish, passionate, soup, happy cooking. Oh, okay. Oh, that's right, I got a new rod. I'm literally a 9th grader. It's fine, you're only like 10, 11, 12, freshman, sophomore, junior, senior. You're only like 7 years away, it's fine. 7 years away. Which, yeah, that is a long time. The amount of things you learn in 7 years. Which, to be fair, when I was a 9th grader, I didn't know anything. I didn't know how to code yet. I didn't learn that until I was like a junior in high school. Because my school in particular just taught us all that stuff really late, or it gave us the option to learn all that stuff really late. Which, my school didn't even have cybersecurity classes. But, you know, the machine learning portion of this lecture is just kind of for the heck of it. It's not really designed to really understand. Well, maybe some of the stuff will stick with me. If anything should stick with you, it's the object-oriented design portion, because that's the part that's really going to help you the most if you do any kind of software development. The machine learning stuff, it's like 90% theory, anyways. I have to program it, but most of the concepts themselves are designed to be complicated. But, you know, you not knowing Java as a 9th grader now actually makes a lot more sense. Because I remember when I was in 10th grade, that's kind of when I started doing like computer science stuff. And they taught us HTML first. Which I don't know if you've messed with HTML, but it's horrible. Like the stuff of old web pages. Kind of terrible. Which I only really learned programming like junior to senior year of high school, where I took game development courses. Which in those ones, we worked in Unity, programming in C#. And that's kind of where I learned most of what I know about programming before I got to college. Oof, not looking forward to that in my networking class. You shouldn't have to. In networking, you shouldn't have to touch, like, a lot of those old programming languages. Honestly, in networking, I don't think you'll have to do much programming in general. And if you do, it's probably something that there's like an environment for that has its own tool set that you can work with. Because at least you're not like, I don't know, well, I guess you might have to play around with like sockets and things like that. Oh, okay. Sockets are horrible. Like actually creating a connection between 2 ports. It's a long process in code, which actually my Unix journal is like right there. I can actually go over the basics of how to encode, connect a server to, or a host to a client. Because I don't know how far your or what networking really covers, but I'm sure some amount of Unix, the stuff I learned in Unix with in terms of like connecting things across the network, I'm sure some of that is probably applicable. I should find what page I put it on. Nope, this is physics. What is this? Central limit theorem? Oh, that's calculus. What else? That's something I'll have to look forward to, calculus. What is this? Intro to CS. What is this? I have no idea what class that's from. Okay, let's keep going. Oh, here we go. Unix. My Unix/data structure. It's a prep course for comp TAA Net Plus. I have no idea what that abbreviation is supposed to be. Okay. Networks. I have an entire set of notes on networks. A lot of it is related to Unix, but it's probably fine. Okay.
なんだはひどくねえか
So if we consider networking, we one consider our internet routers. Cybersecurity certification. Ooh, that's always fun. I never really had much of an opportunity for certifications in high school. I had opportunity for a database certification, but they underprepared us for it, so none of us got it. But you know, cybersecurity is always nice. If it's something you can do well, then it's something that will serve you well. Alright, networks. We'll do it after the cutscene.
そうよ。リオネラが自分から人に話しかけるなんてめったにないのに。
It does give me a time to reread these notes from, what is this, 2 semesters ago? 3 semesters ago?
ごめんなさい。話しかけたらダメだった。あ、違うの。ちょっと考え事してたから。
考え事だ柄にもねえことしてんな
失礼なこと言わないの。それで難しい顔して何を考えてたの？お仕事のことでちょっと最近本を見てると知らない材料ばっかり載ってて、私がいつも行ってるところじゃ見たことないし、どこで取れるのかなーって。
それって考えて解決する問題じゃねえだろ
まあそうなんだけど、錬金術の材料が取れそうな場所、私心当たりあるかも。本当？どこどこ？この国に来るときに通ってきた街道なんだけど、珍しい植物がたくさん生えてたし、もしかしたら街道って旅人の街道のこと？ええ、表向きは普通の街道だったけど、ちょっと裏道に入ったら結構入り組んでて、なかなか面白い場所だったわよ。
今となっちゃ笑えるけどあん時は大変だったな
それは言わないで。
それなら今度行ってみようかな
本当？それでもしよかったらなんだけど、私も一緒に行きたいんだけど。
リオちゃんも？
もう迷子にならないように気をつけるし、それに私もいろんなとこ旅してきたから、少しくらいなら戦えるし。
リオちゃんが一緒なら心強いかも。それじゃあ行くときはよろしくね。
ありがとう。
Yay! More stuff. More people. Okay, I've had a reread of my notes. I think I can do a lot of this stuff without referencing the Unix side of things. Before that, let me make sure everybody is not dying. So when you're dealing with networks, there are a lot of, there are 5 layers that you're working with. The first one being the physical layer. So the actual device itself that will be handling your network. So this is done through the network interface card, the NIC, connected, we'll just say for simplicity by a wire. So 2 NICs, of which they're connected to a computer, such that these computers can basically interact with each other through the network. So that gives us the concept of bandwidth, which are the number of bits per second that can be sent across this network, and latency, which is the time that it takes 1 bit, or maybe not necessarily 1 bit, but for some number of bits to reach their destination. So we always talk about latency. It's basically that extra delay between sending and actually receiving it. Right above the physical layer is our data link layer. So the data link layer is what actually what sends these packets of data across the wire. So it decides. So it basically compresses this data into a packet, which includes the data, the source, and the destination. So that way both sides know exactly, you know, where it came from, who it's going to, where it's supposed to go. So this data link layer sits right on top of the physical layer, and it basically uses the address that's assigned to every single NIC, every network interface card on the physical device. And we'll say, for example, that these NICs, these computers all across the network, are connected through Ethernet. Just, you know, the broadcast media is an Ethernet cable. So, yeah, the data link layer basically just organizes this data and prepares it to be sent. So that leads us to the network layer. Oh, there's an apple.
ただのリンゴじゃないぜ。ほれ。すっげえ酸っぱいだろそれ。って聞いちゃいないか。ほら、水でも飲んで落ち着けよ。悪い悪い、そんなにいいリアクションするとは思ってなくてさ。
まだ舌がヒリヒリするよ。
さて、うちの店で使う分も取って帰るかな。お前もいるだろ。いらないよ、こんな酸っぱいリンゴ。生でかじると酸っぱいけど、火を通すとすごく甘くなるんだぜ。本当だよ。そんな疑うような目で見るなって。それ
じゃあ持って帰るけど、また酸っぱかったら本気で怒るよ。
大丈夫大丈夫。もしそうなったら、そりゃお前の料理が下手だってことだ。
Our apple. Alright, so sitting atop the data link layer, which is above our physical layer, we have the network layer, which is basically our router that connects these networks and actually attempts to send these packages across the network. So if you imagine the kind of setup, you'd have, say, some host system connected across Ethernet, connected to the router. Let's see. Okay, that leads us into IP, which is the Internet Protocol, which is kind of like how we get like IP address and things like that. This protocol basically routes packets across the network and gives each network interface card, each NIC, an IP address, so that way the routers know where to send it to. My notes aren't very detailed, but it's fine. On top of the network layer, on top of the data link layer, on top of the physical layer is our transport layer. This provides a direct connection between your source and your destination, and basically hides all the lower layers, so you don't really need to know they exist. So it has a couple of other protocols associated with it: transmission control protocol, user data protocol. Don't ask me what they are. I haven't written them down. It's been a while. At the very top, we have the application layer, which is actually the application that is going to be requesting to send these packets and actually running all the layers below it. What's this? Domain name system. There's just a lot of stuff. But what the stuff that comes after it is the stuff I'm more familiar with, where how you actually encode send information, so to speak. It's very similar to like actually picking up a phone and doing all that stuff. It uses something in Unix referred to as a socket. And the socket is basically just a thing that was created for exactly communication across the network. So at the beginning you would actually have to find the IP address and find what ports that you're actually trying to connect to. So, for the example of like a game, if it's online multiplayer, where there isn't a dedicated server by whoever made the game, then one player has to serve as the host, the other one has to serve as the client. So one player would host the game on their machine, and it's up to the other player to connect as a client to their system. And with that, they would need to know, in order to connect, the IP address and the ports. How you would get that, I don't know. Just it has to be provided somehow. But after you know that information, you would create a socket. And this socket is basically your doorway into the connector. If you had to create an analogy for it, it's like a phone. The IP and port is like trying to find your friends. Oh, you've worked on it a little bit. Sockets are a pain in the butt. Which I've only worked on them in C, which is even more of a pain in the butt. Yeah, so you would create the socket, and you would connect the socket to the server using that IP address. The means of doing that is the socket figures most of it out for you. Then you would read and write to the socket, kind of like a pipe, and send or receive whatever data you need, and then you'd close the socket. Again, how that's done in a Unix system is like a couple hundred lines of code, but it's not like, if you look at it, it's not like amazingly complicated, but it's also just like annoyingly complicated. Which, yeah, oh yeah, even just finding the IP address and the port is an annoying function. Get address info, which returns the host name, the service, hints some result thing. Oh, it's a list of IP addresses. Yeah, I do not miss this class. Which, if you do like any work in IT, you have to know some amount of Unix, but oh, it's horrible sometimes. Especially since you write everything in C if you're not working literally out of the terminal. Which, if you ever touch C, the programming language, you're gonna have to pull your hair out. Because yeah, out of all the languages I've had to learn, the worst one was assembly. The second worst one was C. Assembly is a whole nother beast. But yeah, it's been a while since I've taken Unix, and I didn't take like the greatest notes because I didn't really need to, I guess. I did fine in the class without like amazing notes. Is C really that bad? Lots of people have recommended it as a starter. If you want to become really good at programming, then yeah, you could start at C. But C is also easily one of the hardest ones to deal with. obviously if it's your first, you're going through the learning curve of programming at the same time that you're going through the curve of learning C. So I guess in a sense it's easier if it's your first. But it does kind of set you up for all the languages that came after it. Because C++ is an upgrade from C. It's object-oriented, where C is not. It's an immediate upgrade of C. Java is an immediate upgrade of C++, designed to be a whole lot easier and much safer. Because that's another thing about C, is that C can potentially teach you like some of the worst programming practices you'll ever see. No pun intended. Because so much of the way it messes with data is like, really unsafe. So, for example, C has something we call pointers, which points to some memory address on your system. Or, yeah, so, for example, you can use it to point to, say, a variable. But the thing about C is that it doesn't do a whole lot of checking. So you can basically use pointers to access literally any point of memory on your machine and, like, screw everything up. Which that's just like one of like worst case scenarios kinds of things, but it's one of the things that Java, when it was created, kind of attempted to, or I say attempted, it did kind of hope to fix. Because the other thing about C is that, again, one, it's not object-oriented, so you have to imagine everything in terms of functional decomposition, which isn't necessarily a bad thing, but it does make a lot of things harder the more lines you're writing. But like I said, I'm also just biased because I learned some of these later languages before I learned C, so C was just like horrible. But in terms of benefits of C, it's really fast. Like in terms of actually like running, it's much closer to, you know, the assembly than something like C++ is. So it runs really fast. And you know, C supports multi-threading and sockets and all this stuff, but I guess it's not like horrible to recommend C starting out, because like I said, you're literally going through the learning curve of, you know, learning programming. At the same time you're going through the learning curve of C, but you have to be careful about the habits you develop while programming in C. Because, you know, it's just one of those things. Programming in C versus programming in like an object-oriented language. Languages that don't support pointers or significantly restrict pointers. There are going to be things that when you reach other languages that there's just not going to be possible. Things that you can do in C that you can't do there for arguably good reason. So, I mean, if I had to pick, like, recommend one language for somebody to learn right off the bat, I like Java, but I think C++ is a good starting point. It basically gives you a bit of everything. C++ supports most of what C can do, yet it also gives you the ability to work with object-oriented programming, things like that. And if you can learn C++, you can easily learn Java. I don't know about Python, but we don't worry about Python. C# you can learn easily if you know C++. Basically, a lot of languages you can learn pretty easily if you know C++. But I don't know. In my case, I learned C# first, but that was out of necessity. So if you don't, I probably would have started with, would have liked to start with C++ if I could have. Or in my case, Java, because I just like Java. But you know, there are plenty of tutorials out there that can get you pretty good and started in programming in any of those languages. Is Python still pretty widely used? I guess so. Yeah, I would say it's still widely used. It has a niche. It does have its niche. If you can avoid Python for as long as possible, I would recommend it. Something that a lot of us in CS like to joke about is that in Python, you're not doing a whole lot of coding. You're just stringing together libraries and basically code that other people wrote to make yours work. And Python also has a lot of other weird quirks to it. For example, how it handles its data types, which... how do I describe this simply? I don't think there really is a simple way of describing it, unfortunately, but... Python is just really different. But as far as is it still being used? 100%. Python is one of the only ones I actually used. Yeah, I mean... I don't know. I've never liked Python. I've learned Python at one point. I was like... It's just okay. I mean, but again, I'm biased. But like I said, if you had to learn any language, I think C++ is definitely a good one. Especially since a lot of languages have kind of built off of the C suite. Which I do know Python is used extensively for things like AI, where it's a lot of data processing, but also in that same vein, you also have to use Prolog, which is even worse. But yeah. Yeah, I mean, everything you can program in C is possible to program in C++ to some capacity. Obviously, there are going to be some things you physically can't do, but C++ is like a lot of the good stuff of C plus some. Also, it's so much easier than C. Which, in university, they teach, well, my particular university teaches C++ over the course of like 2 semesters, but the majority of the actual meat comes from like basically 1 semester. So learning it really isn't hard. But yeah, it's like one of those things, the more languages you learn, the easier it is for you to learn a new language if you have to. Like if you just happen to get a job that needs you to program in like Ruby or something weird like that. And, you know, the more languages you've learned, the easier it would be for you to just kind of pick up and start learning whatever this new language is. But yeah, it's a process. Which, with some mildly rigorous study, you can easily get proficient in C++ in not even a year. But, you know, necessity drives innovation, so it helps to have something you want to accomplish with your programming to basically kind of apply to. Like in my case, I made games, so I learned how to program. Or in other people's cases, they wanted to learn how to make websites, so they learned how to program in JavaScript or things like that. So just come up with, just stuff that you can only do by programming and just kind of run with it. Because the only way is to learn by doing. What kind of games did you make? During my first during my video games programming course that I took in high school, I made like a 3D game because most of what we learned in the Unity tutorials was 3D stuff. But it was like you controlled a guy in third person and he can shoot. Just the standard stuff, third person. And there were like a series of it was basically just boss battles, just a boss rush. You would just walk to each part where the bosses were, you would beat all 3 of them, and you would win the game. This was like really early on, where I was still learning how to program and all that stuff. So it didn't look very nice. It was submitted for, a project for the class. Nobody could beat the third boss. It's like ultra kill. I need to Google what that is. Oh, I got a lot of Discord notifications for some reason. Gargura's getting a new outfit. Discord stuff, okay. Let me Google what ultra kill is. Oh. That one's first person. I guess that one does have a toggle for third person. Well, but yeah, so it only had 3 bosses, and it was something I only had enough time for, like, I had like half a semester's worth of time to work on it, so it wasn't like amazing. But that was kind of where I started. Nobody could beat the third boss. I could beat it just fine, but nobody else could beat it. But after that, when I started working on my own projects, I started making an RTS, a real-time strategy game, where it was like soldiers and all that stuff. That one is still actually currently in development, because it's evolved kind of 2 different times. Who only the creator could beat. It is very possible. It's a very possible game. They just couldn't do it. It's not my fault they didn't have like an hour practice that I did. But yeah, I've since lost the files for that game. The one that I made for that class, because we had school devices and I only had it saved on the school device and stuff, and things and stuff, It is what it is. But yeah, so the one that I started working on over the course of the several summers since I graduated high school, it was involved in RTS, where you control soldiers and generate resources and try to kill each other and all that stuff. So originally, I had my very limited programming knowledge make something kind of bad, like in terms of like the base functionality, which most of it didn't get done because I only had 1 summer to work on it and I was working full time. But when I started college, I improved my programming and it got a little bit better. And then I started working on it again, and I discovered something from Unity. Because Unity is like one of the 2 major game engines. And generally, making games also follows object-oriented principles. Like a lot of things that exist in a game you can imagine as an object, and you can operate on as if it were an object. Like it literally has a class called GameObject that serves as the basis for everything you see in the game. But Unity also has another system referred to as Unity Dots, which is its data-oriented technology stack, which basically is another method of programming aside from object-oriented called data-oriented programming, which is you evaluate things in terms of just pure data. So you completely get rid of objects completely. And the one benefit, if you're willing to deal with how difficult it is to program in and how unintuitive it is, it has like serious performance. So it's the code for Unity all open source. It's not open source, but it is free. If you want open source, you have to do like, what is it, Godot, or whatever it's called. But Unity you can work on for free, as long as you stay away from the 6.0 release. Then, as long as your game doesn't make like, I think it was like $100,000 or something, then the tools are completely free. Hence how we were able to program using Unity in school. But yeah, so the data-oriented technology stack is something that's kind of new. It was only within the past couple of years that it actually hit its 1.0 release. So I've been learning that system, and it's significantly more challenging than object-oriented programming. So it's kind of taken a little bit longer, but it has gotten. There are more of the core functionality, operational kind of, but it's a long process. Game development is an incredibly long process, especially while doing school and working part-time, or at least during the summers I work full-time. Have you seen the crazy new Unreal Engine body cam games they made? Oh no, what have they made now? I have no idea what this body cam stuff is. And I'm scared. I think there's more stuff. Alright. Which I know Unreal always gets up to some weird stuff.
ロロナ、確かお前は一人っ子だったな。
はい、そうですけど。何ですか、突然。
いや、特に深い意味はないんだが、弟か妹が欲しいと思ったことはないのか？
They made a body cam shooter that looks nearly identical to Lista's. That's funny. That is kind of funny. The graphics are next level, yeah. Graphics was always one of the huge pulls for Unreal. In exchange for its extra complexity and working in, I think, C++, you get, you know, basically access to their extreme graphics tools. I've never worked in Unreal. I probably never will, because I still haven't mastered Unity. But Unreal can get some pretty crazy stuff done. And I know a lot of people that I go to college with that will swear by Unreal and will never use anything other than Unreal, but you know, at the end of the day, a tool is just a tool. You can make any of them work. It's just how much work are you willing to put in to actually make it work. The difference between using like a power tool drill versus just a simple hand drill kind of thing.
そうですね。昔は欲しいって思ったこともありましたけど、うちのお父さんとお母さん
しょっちゅう二人きりで出かけちゃうから一人でお留守番してるのが寂しくて。
ではもう一つ質問だ。これはあくまで家庭の話だが、もし弟か妹ができるとしたらどっちがいい？
そうだな。
Oh, I get to choose.
妹かな。女の子同士の方がいろいろ一緒に遊べそうだし。
よくわかった。参考にさせてもらおう。
What do I consider take into consideration?
参考なの？また何か企んでるのかな。
Okay, I think that is a good spot for today. I didn't get to do my database lecture, but it's fine. That one I can just pick up whenever I want because the story behind it is so funny. Yep, thanks for joining. Listening to me ramble. Yeah, I'm going off to bed. So am I. I have work tomorrow, so I do have to sleep eventually. Alright, well you have fun. And for everybody else in the future, I'll be around.